Hello there. Our next presenter is Stephen Arrowsmith from SMU. He is using explosions from a munition plant in Oklahoma to probe the atmosphere with infrasound pulses, which is pretty interesting, and track down some pretty elusive phenomenon. Stephen?
Thanks, Larry. So infrasound is sound that's lower frequency than we can hear. But what's cool about it is it travels really long distances. So we can measure it a long distance away and use the sound we measure to say something about the atmosphere it travels through. So if we think about all the phenomena in the atmosphere, it spans a very wide range of scales, both in terms of spatial scales and temporal scales. And this figure shows that the two are related. Phenomena that span really large spatial scales take much longer periods of time and different temporal scales. So we can think about phenomena all the way from global circulation patterns down to turbulence, very fine scale turbulence. And the sound we measure, the infrasound, have wavelengths of tens to hundreds of meters. So we can use this sound to resolve everything from about 10 to the minus 1 kilometers and up, and from about 10 to the minus 2 hours and up. And what this means is we can resolve structures in the atmosphere or phenomena that are not currently resolved in meteorological models, which typically have a resolution of about 1 hour. And what's not captured in this figure is that there is also a vertical component to this. So we can use infrasound to measure phenomena at higher altitudes that would be resolved at the ground but aren't at higher altitudes because we don't have direct measurements there. And in particular, I want to highlight gravity waves. These are a phenomena that we're going to study. So the US Army have a facility in McAlester, Oklahoma, where most days they set off about 60 explosions. And they do this as a way to basically destroy old munitions. And this is a really cool laboratory for us because basically we have a series of explosions separated about 20 seconds apart in time and occurring in a very small area. They do this over 2 pits, which are a few kilometers apart. And they put all the munitions in each pit, and they set them off with 20-second delays. And these are measurements of the acoustic waves from these 2 areas. Each spike here is an individual explosion, and these are measurements that are made very nearby. What we're interested in is the sound that we measure at long range, and in particular, the sound that we measure at about 200 kilometers away. Because at that distance, we can measure these, what I'm showing here are ray paths, which are just showing predictions of where sound will go. So if we have a source here at 0, 0, we're looking at the infrasound that travels up into the stratosphere, and it gets to about 40 to 50 kilometers above the ground. And then it refracts back to the ground. And we're going to measure the infrasound we measure here. So the waves we measure are sensitive to phenomena, at these altitudes. And this map shows our experiment. So the 2 pit areas that I showed are the red stars here. The measurements we made at the MCA, which I showed just before, are local measurements. And I'm going to show the measurements that we've recorded here at WCT. This is at the Wichita Wildlife Refuge, which is a very beautiful place if you ever get a chance to visit. It's about 250 kilometers to the west. And so what I'm showing here are the measurements we made from one of these shot sequences. And so the important thing is you can see that we can still measure each individual shot. So the 60 explosions, we have 60 pulses here, each pulse corresponding to a different explosion. The amplitudes are much less because the energy has basically been lost or dispersed as it's propagated. So it's about 2 orders of magnitude lower. Now what we've been able to do, because we have a measurement at the site and we have this measurement at 250 kilometers away, is remove the effect of differences in the source from our observations. So not all the sources are identical, but because we have a location where we measure the acoustics right on site, we can remove that. And so we can look at the effect of the atmosphere only. And so here what I'm showing now are the observations at 250 kilometers. Each vertical line is a different explosion, and so this is organized by detonation time. And if the atmosphere wasn't changing, each one of these wiggles, each one of these vertical lines would look identical. But they don't. And the reason they don't is because there's phenomena, some of this fine scale phenomena that's happening over time scales of seconds that's affecting our signals. And these are gravity waves in the stratosphere. And we're able to use these measurements to basically tell us about the period of these phenomena and the amplitude of these phenomena. And that's my story. Thank you.
Okay. It's interesting to me the way you detected it. And Oklahoma is, I've never been to Oklahoma, so I can't verify this for sure, but it's fairly flat.
It is.
Would you expect that terrain would have any kind of impact on how you're going to be able to use infrasounds?
Terrain definitely can have an effect. At these sorts of long distances where we're 250 kilometers away, it tends to have a pretty minimal effect, actually.
So, and the explosions that were going on at the munitions plant were just part of their normal everyday
Yep.
thing? Okay.
It's an everyday thing.
Question from the room.
Yeah, so when this infrasound is going into the atmosphere, what is it refracting off of when it comes back?
So basically, that's a great question. The temperature in the stratosphere increases because of ozone. So ozone absorbs heat from the sun. And that increasing temperature causes the sound speed to increase. And so because of Snell's law, it basically causes the waves to get refracted back down to the ground.
Okay, thank you. And then how do these infrasound measurements kind of compare to radar, and how can they improve what we know from radar?
It's really measuring a different thing. I mean, one of the nice things about acoustic measurements is that they're totally passive. So, we can just put a sensor out there, it sits and it records, nobody would know it's there, and we can come back and make the measurements later. Radar, there are ways, of measuring properties of the atmosphere, but they require, power, they require a lot of energy, and they don't necessarily always provide continuous measurements.
Gotcha. Thank you. And then what is the implication of being able to learn about these gravity waves using this method? Can this be used in weather forecasting or in understanding other atmospheric phenomena?
Yeah, so one of the limitations, I would say, of weather forecasts today is that they're based on observations in the troposphere, the lowest layer of the atmosphere. But we know that there is mixing between the stratosphere, the next layer up, and the troposphere, and these gravity waves play a role in that. So the better we can understand them, the better we will be able to make longer range forecasts than we presently can.
Thank you. And we have one more. Is there any way to employ this technique in a more general way? This question asker says, I can't imagine that most neighborhoods would appreciate these kind of explosions nearby.
Yeah, that's a cool question. I'm glad somebody asked that, because what we really ultimately would like to do is use ambient noise to do this. And so the oceans are continually making infrasound all over the world. In this particular case, we have this very nice controlled laboratory, and so we want to practice on this. But if ultimately we can make this work here, then we want to move to, can we just use the natural sound from the oceans to do the same thing?
Okay, thank you. We actually just got one more that came in. Did the waves change the temperature profile of the stratosphere as they pass through it?
No, they basically don't.
Okay, thank you. I think that's it for over here.
Okay.
Thanks.
Any questions from the room? Don't go anywhere yet.
Okay.
All right. Thank you, Stephen.
Cheers.
Really appreciate it. We're going to take a short break, and we'll be right back.